Okay, so I was a student of Krishnamurti starting 27 years back. He introduced me to the Mott transition, and quite embarrassingly, I've been doing it for the last 2 decades. There's also a lot of Chandan, as you will discover when we go along. I mean, first, he taught us many-body theory, Diptiman taught us quantum field theory, but more recently, work done by Shumilan, Chandan, and TVR has had a lot of impact on the kind of thinking that will show up in the solution of the Mott problem, which is basically to say there is, if you wish, a classical theory at the background of a quantum theory, and it creates a great deal of insight in understanding quantum phases like magnets, superconductors, and Mott insulators. So this is a mixed audience. There are technicalities I'll try to sort of breeze through, but let's hope the basic message gets across. So the idea is to take you quickly through an introduction on Mott physics and frustration. Shubhra has already told you about frustration in great detail. Then the pyrochlore Mott transition, the sort of simpler case study in this talk. Then argue that there are actually experiments. This is not a theorist game. Experiments on pyrochlore structures, which require little more complex a model than the Hubbard model. Interpret those answers in the light of what I call spontaneous disorder as a concept. It's a bit tenuous, but useful to start with, and then conclude. So this is a mixed classical quantum audience, but I'll pretend that everyone has some idea of what the Mott transition is. It's interaction-induced localization of electrons. And once the electrons localize, they behave like local moments. They form magnets of the kind Shubhra was describing to you. Much of the current understanding of the Mott transition goes back about 20-25 years to something called dynamical mean field theory. I mean, the ideas behind the Mott transition have been around for 50 years maybe, but a quantitative theory is based on DMFT. The naive version of DMFT, the original version, ignores spatial magnetic correlations. So it gives you a generic description of what the Mott transition is without bothering too much about the dimension dependence or the lattice geometry dependence of the phenomena. Now these effects, dimensionality and lattice, dictate the critical interaction for the Mott transition, varies from 2 to 3, triangle to square, etc. The magnetic character of the Mott state, whether it is ordered or a spin liquid, and obviously quasi-particle properties near the Mott transition. So it's good to get a generic theory to start with, but to describe real materials, I think these aspects need to be built in. So people have not been sitting idle. There are attempts to generalize DMFT to cluster DMFT, dynamical cluster approximation. This is Krishnamurti's contribution to build in correlations. But even then, as we will see on frustrated structure, I mean, if you can anticipate the nature of long-range order, these kind of approaches take you some distance. If you cannot, for example, on structures like the pyrochlore, then a more spatial approach rather than an embedding approach may be useful for studying the Mott phenomena. Now, Shubhra has taken you through this, so it's just a 2-slide breeze through. Frustration is when local minimization of interactions is inconsistent with a global minimum. We don't need to belabor this. And this shows up in magnetic systems where triangular motifs are present because the elementary triangle is the first violation of this requirement. And these are structures. So this is the kagome, the checkerboard. My structure would be the pyrochlore. And they involve corner or edge sharing triangles in 2D and tetrahedra as the elementary building blocks in 3D. And if you consider the Ising model on these lattices, all of them have non-ordered, highly degenerate ground states. Now, what's the connection of this to the Mott problem? So the spins we talk about in this problem in real life would actually arise out of correlation effects in a Mott insulator. So most frustrated magnets are actually Mott insulators in the so-called limit U by T much greater than 1. You look at a model where there is hopping on a lattice, the kinetic energy, there is a strong local interaction and the number of particles is equal to the number of sites. If the U become large, real hopping of particles is inhibited, what you end up is with the Heisenberg model that Shubhra described to you. In the deep Mott insulator, when the U/T ratio is much greater than 1, this is a leading term that describes the physics of the system, a short-range Heisenberg model, and if you had a Kagome, a triangle, or a pyrochlore structure, the frustration in this is obvious. My question is different. I want to sort of move on a different axis. So what happens when the U/T ratio is reduced, either by physical pressure or by chemical substitution? There are two effects you can visualize, that if you were starting from the atomic limit, the leading term is a short range T squared by U. As you go to higher order in T, you generate multi-spin couplings, and the size of the moment, which sort of defines the sigmas, itself reduces as you head towards the critical interaction. Beyond the critical interaction, you have a metallic phase. So are there real materials where this kind of phenomena of metallization of a frustrated magnet, Mott insulator, is realized? Well, there are multiple examples, in fact. So the most famous, the well-studied examples come from the 2D organics, the triangular lattice based on the BDD family, where both physical pressure and chemical substitution of bromine from chlorine, etc., can metallize what seems to be a 120-degree ordered Mott insulator. Less studied are 3D variants, the FCC lattice, which again is ordered. I mean, despite the frustration, there is a degree of residual order that one observes in this. For me, the case would be the pyrochlore lattice, where there is no order at all. So I will ignore these two, where despite the triangular motifs or the tetrahedra, the system manages to generate long-range order for Heisenberg spins, and focus on this kind of a structure, where you end up in reality with a quantum spin liquid. In my picture, it will turn out with a classical spin liquid. Yeah. So there is, look, there is a JJ prime ratio on this. So if you if you examine the phase diagram, if you examine the theory phase diagram, there is a window of J prime by J over which a 120-degree phase is stabilized, and there is a short window, a narrow window, where it's believed to be a quantum spin liquid. So there are both, if you wish, realized depending on which particular combination of ions you choose in these. So this pyrochlore Mott is not quite the molybdate example I gave you. That will come up down the line. But we need to build up to the complex case. So what's the model? The model is simple. It's again hopping on a pyrochlore structure with a chemical potential adjusted to give you half filling and a strong local repulsion. How would you approach this problem? Well, you could use cluster DMFT. Doesn't seem to have been used to the extent I know for the simple pyrochlore. But we want to sort of push an approach, or explore an approach, where we retain the spatial and internal symmetries, retain the pyrochlore structure explicitly. Internal symmetries meaning rotation invariance of the problem. Do not presume any specific kind of magnetic order. Okay. There is anyway no obvious long-range order one can think of in this material. So let the system choose what kind of magnetic state it wants, and hopefully use a technique that accesses transport, spectra, dynamical properties, blah, blah, blah. How would you go about doing this? Well, you write a functional integral, begins to become technical, and because of the quartic term you can't quite solve it, you introduce auxiliary fields to decouple. With the next slide will show us how this is done. So let's sort of move to that. So the U term creates a problem for us. And this decomposition of the U, trying to linearize, if you wish, a quartic fermion term in terms of fermion bilinears, goes back actually to Hubbard, reinvented by Heinz Schulz, and in a somewhat less known paper by Tivier, about 10 years back, this sort of keeps resurfacing. that let's try to construct a theory in terms of auxiliary variables which allow us access to the magnetic phenomena near the Mott transition. So we introduce a scalar field called phi, a vector field called m, to retain the rotation invariance of the parent model. And if you run through this, you will end up with a Lagrangian which has the old kinetic part, and something like this. It is the density of fermions coupled to the phi, the spin of the fermions coupled to the m's, and of course stiffness terms. If you take a static limit, these phi's and m's are supposed to be fluctuating, imaginary time fluctuating fields. So this problem is in no way simpler than what we started with. To make headway, one approximates the phi's and m's as static but spatially fluctuating, in which case you end up with an effective Hamiltonian of this look, somewhat simpler in the next page. The parent model, where you had electrons interacting with each other and moving from side to side, now looks like the kinetic term, and simply the spin of the electrons coupled to an auxiliary magnetic moment. Now this problem would be fully specified if you told me what the m's are. So what is the m distribution? Who gives me the m? Well, the m has an effective Hamiltonian which looks rather awkward. It has a component having to do with the free energy of electrons in the m background, a rather roundabout statement, and the usual stiffness part. So this is the so-called trace log g part of the free energy of the Boltzmann weight for the magnetic configurations, and this is the stiffness. Now the second term certainly doesn't make too much sense to someone seeing it for the first time. I'll try to make it more explicit in the next slide. The structure of the theory, and this is the important part, is to rewrite the parent interacting many-body problem in terms of non-interacting fermions in a disordered, here a magnetically disordered background. And the backgrounds themselves, the m's, are determined by a Boltzmann weight dictated by the electron free energy. So two simpler problems, if you wish. This is a problem of disordered fermions, and this, if you wish, is in some sense a classical statmic problem. You trace out the fermions order by order, you end up with what looks like a Ginzburg-Landau theory. So two simpler problems replace the parent many-body problem. They have to be solved consistently, iteratively. The method, I mean, if you ignore all the song and dance at 0 temperature, this is just unrestricted Hartree-Fock, but it's far more sophisticated at finite temperature, where it builds in a family of classical fluctuations. To move to this, so this is an Anderson model, if you wish, Anderson model of disorder, magnetic disorder, coupling to the sigma of the electrons. What dictates the m's? If you were to expand out this object in various limits, you end up with something like this, that if the interaction strength were weak, I can expand in the interaction and end up with what looks like RKKY plus RKKY prime, etc., in the metallic phase. So these would be long-range interaction between weak magnetic moments when you're in the metal. The magnetic moments would have to be induced. They're not there to start with. While if you're in the strong coupling limit where the moments exist to start with, in the atomic limit, you will get a local part which has to do with the size of the moments. This is Shubro-Heisenberg term, and there are additional four-spin interactions, etc., that come up to higher order. So basically, these are approximate forms of effective magnetic Hamiltonians on the metallic side, or the small m side and the large m side, and the fermions are coupling to these moments to generate their density of states, transport, etc. Absolutely. So if you take the nearest neighbor version, you will get the nearest neighbor Heisenberg model. So this is a bit of intuition about the structure of the magnetic model that arises from tracing out the fermions. What do fermions do, sort of coupling to these objects? So if you get back to the parent problem meaning the quote-unquote Anderson disorder kind of object, these were mobile electrons coupling to those magnetic moments. If the magnetic moments don't exist, you get back tight binding. Silly problem. If the moments exist but are small and uncorrelated, you will get a weakly scattered metal. We will see examples of this in the transport that shows up in the metallic phase. If the moments are moderately large but uncorrelated, unordered if you wish, you end up with a pseudogap phase. It's sort of a much desired phase in many correlated electron systems. If the moments are large, which happens if the U is large, then you get a split band Mott phase. And of course, the correlations between the moments or the structure factor that you find in the magnetic sector indicates whether there is any magnetic order or not in the problem. So in your two-stage problem, if you're lucky to be working either deep in the metal or deep in the insulator, you have an explicit form for the magnetic Hamiltonian. You can study this by Monte Carlo or whatever tools you have and work out the magnetic structure, feed it onto the electronic sector, work out. Typically, close to the transition, there is no such neat-looking problem, and you have to iteratively solve the fermion and magnetic problem simultaneously. What does it lead to? So what is the consequence of this in the pyrochlore problem? So in the pyrochlore lattice, if you go through this process, you discover that as you increase the strength of interaction in the model, beyond a critical value, whatever it may be, I call it UC1, you begin to see a weak increase in the value of the typical magnetic moment. They appear at UC1, grow with increasing U, and there is a sharp change beyond which it seems to tail off to 1 slowly. The moments, if you examine not just the size, but the structure factor associated with the moments, there is no long-range order. So within this picture, it generates what one would call a classical spin liquid of small moments here and large moments here. Because there are disordered magnetic moments in the background, the resistivity becomes finite in the ground state. And in fact, the resistivity, when you compute it, is 0 below a certain value, below this UC1, and then increases in a certain manner and blows up when you go to some value called UC2. So this, at some large enough value of the magnetic moment, a Mott gap shows up in the spectrum. Because of the vanishing density of states, the resistivity goes to infinity. And this is the picture of the Mott transition. So somewhere here the Mott transition occurs. The curiosity is, what is this phase to the left of the Mott transition? This seems to be a finite resistivity metal coexisting with small, sort of moderately large magnetic moments. This is interesting, and its fate is a bit ambiguous. Whether it will really survive in the final model is not clear, but this is something we will keep focusing on for the rest of the talk. This is 0 temperature. There is a variant of this at finite temperature as well. Okay. Yeah.
So is this effectively Anderson problem, right? When you are looking into the electron.
Yes.
And you are looking at 2D. So each you are looking 3D. Okay. Okay.
We did it for the triangle as well, but in the triangle there is no such disordered phase. I mean, Krishnamurti did it on the triangle. On the triangle, you get an antiferrometal and you get an antiferro insulator.
Okay.
I mean, a parametal, antiferro insulator, antiferrometal. There is no disordered phase.
I mean, if you have each snapshot is like an Anderson insulator, right, in 2D.
Each snapshot, yes.
So none of the snapshots should have any transport. But so how, when you average, how do you generate?
No, firstly, this is not 2D.
This is not, but okay.
This is not 2D.
Yeah.
So no. My answer would be that in the 2D case, we don't. Maybe we'll come back to 2D later. Okay. So in the 2D case, you get either parametal, a trivial tight binding metal, or an antiferrometal, okay, which is again infinite conductivity, or an antiferro insulator, which is perfectly insulating. So there is no finite resistivity phase within this calculation in 2D. But you can ask the same question in finite temperature, because now there are fluctuating moments. So fluctuating moments would lead to effective disorder. So does it mean that under all conditions I get an insulating state in 2D? Okay, so there you have to invoke some inelastic scattering rate, which will cut off the localization effects at some length scale. But coming back to this, since you're in 3D, those sort of objections don't really hold. Yeah. What would you look like? I mean, what would you examine to look for? you would get an anomalous Hall response in this because we haven't computed it. In the molybdates, there is an anomalous Hall. Okay. In the real material, in both the iridates and the molybdates, there are materials which show spontaneous anomalous Hall related to spin chirality. Okay. So these, I mean, to say that they're disordered, I think is a bit disingenuous because they are on a tetrahedron. There is a certain short range correlation to it. It generates a chirality, as a result of which there is an anomalous component to the Hall, spontaneous anomalous component, that will show up here. The point is whether this survives or not is a big issue, given that you're in a metal. But modulo that, yes, you would see that. Okay. This is the finite temperature variant of this, showing that there is a UC1 at which moments form. Metal, if you believe this, pseudo gap phase, and then an insulator at UC2. There are no finite temperature transitions in this problem. Had I been doing it for the cubic lattice, for example, there would have been a line defining the antiferroinsulator versus the para-insulator parametal. So, finite resistivity at zero temperature. In fact, this is the first instance within this calculation of spontaneous disorder emerging due to frustration, if you wish. This, which blue line? This blue line is where, hello. This is, I mean, if I looked at d rho dt positive and negative, okay, to the right is d rho dt negative and positive. So it's a finite temperature extension of the metal insulator transition. Yeah. Yes. Yes. For which lattice would you want to do it? For a 2D square lattice, let us say? For a cubic 3D lattice, the point is for a cubic 3D lattice, there is a nesting feature. So if you take a T-only model, that any value of u, you're going to get a magnetic moment. Okay. So yeah, for honeycomb kind of an object, there is a finite u, beyond which, I mean, similar to whatever, you probably will not get any order at all. If you did this kind of a treatment, which is a Hartree-Fock treatment on the honeycomb lattice, you probably end up with a finite moment generation point and then a disordered phase beyond it. Okay. So if you looked at the finite, I mean, even if I don't manage to get through all the molybdate story, this is an instance of, if you wish, a spontaneously broken translation symmetry due to the frustrated, okay, due to the emergence of quasi-random magnetic moments over a certain window here, leading to a finite resistivity phase. In terms of resistance, what one would have expected is that in the metal, because of translation invariance, I go to 0 as t goes to 0. In the insulator, I go to infinity. There is nothing which should end up at a finite value. Finite value implies something has been broken at t equal to 0. There is a source of elastic scattering, which you don't expect until something very strange happens in a parent translation invariant model. Now, whether this will survive the quantum fluctuations ignored here is another matter, which I'll come to at the very end of the story. So this is to say that if you probe the spectral features in the transport by your sampling procedure, you get a pseudo gap which deepens with increasing temperature in the metallic phase. You get a gap which smudges out with increasing temperature in the insulating phase, and you can look at angle resolved spectral functions, optical conductivity, etc., etc. So the upshot of all this is there seems to be a disorder arising from the presence or emergence of frustrated local moments in this kind of a model and this kind of an approximation. What is the experimental situation? How long do I have 5 minutes. So experiments. The experiments, unfortunately, are not on the simple, are not a realization of the simple Hubbard model, but have additional degrees of freedom. So these molybdates, this R2, rare earth Mo2O7, live on a pyrochlore lattice. And if you vary the ionic radius large, crudely is like large hopping, small u by t, and this, if you wish, is your large u by t. So at small u by t, it's not a parametal, it actually is a ferrometal in its ground state. The ferro is unusual in Mott insulators, but has a simple understanding when we sort of go to the next slide. However, if you go to large values of so this is insulator, this is metal. The metal, rather than being a parametal, is a ferrometal. The insulator, rather than being antiferromagnetic, which anyway is not allowed on this structure, is a spin glass insulator. And the typical scale for this is about 100 Kelvin and about a 20 Kelvin scale for the spin glass insulator. If you look at the transport insulator, so these objects, dy, tb, gd, blow up as t goes to 0, nd seems to go to a small value, sm goes to a value. Now, would I attribute it to spontaneous transition symmetry breaking or extrinsic disorder? Hard to say. But nevertheless, there is a clear example of something like this showing up with a resistivity roughly like 10 milliohm centimeters, a fairly large number for a metal. This is the map of the optical spectral weight, saying if you're in the insulator, you gain spectral weight on heating, low to start with, gain on heating, high to start with, lose on heating, and end up with sort of a fuzzy looking object at high temperature. Now the usual Mott transition, the usual in the Hubbard language, is from a parametal to an antiferro insulator. Here it is from a ferro to a spin glass insulator, residual resistivity, etc. So you can also, unusually for a Mott insulator, see a field-driven transition. If you were to look at this object, which is on the verge of the insulator-metal transition, and apply a magnetic field, you get a huge magnetoconductance. In fact, the resistance falls, this is the 10K resistance, falls by a couple of orders of magnitude. That is again because you're in the proximity to a ferromagnetic phase, and the phase computation is tilted in the favor of magnetic order when a magnetic field is put in. So the mystery again goes back to how did you manage to get a ferro phase adjoining a spin glass or a spin liquid insulator in this kind of a material. If it did exist, then annealing out the spin disorder and getting a large magnetoconductance itself is not a mystery. Anyway, so what are the issues? So how does one get spontaneous disorder? If at all one were to think of these phenomena in terms of spontaneous disorder in the clean system, what dictates thermal scales is not very interesting for us right now. And how do you understand the large finite resistivity, Anderson-Mott field-driven transition, etc.? Also spin correlated driven anomalous Hall, which we are not going to get into. Write a model. So we will be quick on this. Unlike the parent Hubbard model, which had one orbital with electrons hopping between sites and a local correlation, this has a deep level which behaves like a magnetic moment. So the effective degrees of freedom on the molybdate are not just one orbital with up and down spin, it's basically a deep level, a so-called A1G level, which behaves like a magnetic moment, essentially localized, and a orbitally degenerate EG prime state up here. So I would have to write a model which has this S degrees of freedom in the background, not to be confused with the M's which come from the Hubbard-Stratanovich, and a twofold degenerate alpha beta level sitting up there. So the description, very messy, looks like a two-band, two-orbital kinetic energy. It has a Hund's coupling between this object and this object, between the A1G and the EG electron. It has an antiferro coupling between two local moments on neighboring sites, and it has the usual Hubbard terms in it. Now, I will push, for the sake of convenience, this Hund's coupling to a large value, so that I'm not worried about the electronic spin anymore. I'll look at the spin polarized, like in the manganite problems. If you went through all of this, you'll end up with a model which has a simpler structure. It has to do with the orbital interaction between two electrons on the same site. The spins are parallel, so there is no up-up interaction anymore. So there is an orbital Hubbard model, a spin-dependent hopping between sites. Why is it spin-dependent? Because to move from this site to this site, you need to bother about what the core spins are doing. Sort of again, reflection of what one saw in the manganites. Large Hund's coupling forces this electron spin to be parallel to this electron spin. These are antiferrocoupled. So the underlying magnetic state of this is going to dictate the hopping of these electrons. As a result, the hopping picks on a complicated form here, depending on the angles at neighboring sites, the two orbital Hubbard interaction, and an antiferrocoupling. Now, in contrast to the older problem where you decoupled enough end-down interaction in terms of a magnetic field, here you will introduce what is called an orbital field. So I call something a gamma coupling to the orbital moment of the electrons. So the complicated looking kinetic energy, depending on the relative core spin orientations, orbital moment, my auxiliary field, coupling to the electronic orbital variable, coupling to the orbital moment, and the antiferrocoupling. This is a charge, unlike the older problem, which was a charge spin problem, this is a charge spin orbital problem that you have to solve for a particular choice of U and JF. So you again go through the annealing process, the Monte Carlo, etc., to anneal the background magnetic moments and the auxiliary variables and try to find out what happens. So it looks like a spin once again. There's only one U because you pushed out the U prime using the very large H. Okay. So spontaneous is sort of back again. And what are its effects on this problem? Longish text, it says the U and the JAF conspire. U suppresses kinetic energy, inhibits double exchange, aids antiferrocorrelations if you wish. So the magnetism, the ferromagnetism is aided by the Hund's coupling and kinetic energy, but the U and the JF are sort of opponents of that. So either if you go to large U or go to materials with an effective large JF, the ferromagnetic tendency is suppressed in favor of the spin liquid, spin glass character. The orbital order or the orbital degrees of freedom are the equivalent of spins in the parent Hubbard model, and in the deep Mott phase you will end up with an orbital liquid rather than a spin liquid. So the orbital variables are not going to be simple antiferro because they live on the pyrochlore, and you will end up with this peculiar looking short range correlated phase there. And the charge physics, if you are at very large U, the orbital moments will gap out, lead to a Mott phase. If you are at very small U, well, you will get some kind of a bad metal. In between, the so-called Anderson-Mott regime, the electrons are subjected to orbital and spin disorder, and the combination of this leads to a physics which is more amplified compared to the old version that we saw in the Hubbard model. So this is Hubbard prime, if you wish. Oh, not bad. Consequences. So you have now two variables. You can vary the U in the problem, and you can also vary JF. And thankfully, in the real materials, you can apply pressure and you can do ionic substitutions, which seem to probe this two-dimensional phase diagram. Not cleanly, I mean, it's not that one of them varies T by U, the other varies JF, but in a manner you go over a two-dimensional parameter space. So if you don't have any JF at all, there is no competing antiferromagnetism. Everything is ferromagnetic. You had a ferroinsulator to a ferrometal transition. At their surprise, the moment you put in a JAF, increase its value, the left-hand side corresponding to small t or large U begins to become a spin liquid insulator. I don't get a spin glass because there is no extrinsic disorder in the problem. If you had put weak extrinsic disorder, this probably would have frozen into a glassy state. But within the scenario I'm working, I don't seem to see any freezing transition at all on cooling down the system. But spin disordered and orbital disordered in this neighborhood, and that seems to have a dramatic effect on the transport properties that we observe. So firstly, a comparison with experiments. This is a bit of a show-off. So if you calibrate your parameters in the light of what density function theory tells you and compare transition temperatures and magnetic moments, notice there is a factor of 2 here. Modulo the factor of 2, which I'll justify in a moment, you see that the character of these curves, this versus this, I don't get a spin glass because of the absence of disorder, is not terribly different. the magnetic moment in the ground state, if I'm in the metallic phase, I get a large moment. As I go through the transition in the insulating phase, I get a small but still finite moment. Doesn't do too badly between theory and experiment. Now you can ask, a factor of 2 hardly is a wonderful match. It turns out that when you use a Hund's coupling infinity, it increases the kinetic energy in the problem, in contrast to Hund's coupling, which is really 4 or 5 in the real material. So if you could do a 2 orbital 2 spin calculation rather than a 2 orbital 1 spin calculation, you actually push this down by a factor of 40% to 50%. I mean, it's a more tedious calculation, but the qualitative physics is a proper choice of Hund's coupling and the parameters used here probably will give you transition scales which are also consistent with the experiments. Transport. So you saw these curves before, blowing up, going to a small value, if not 0, and an intermediate value here. These are color-coded to be sort of identical to each other. More insulating than in the experiment, but still blowing up, going to a finite value. These are all finite. In fact, you notice that if someone could make a crystal which had GDSM combinations in it, trouble is it will introduce disorder in the problem. But if you could bandwidth tune, then you will get an unusual family of resistivity curves with increasing 0 temperature values and a very odd looking temperature dependence. So these are consequences of your increasing spin and orbital disorder as you go from this end of the material to the upper end. We're almost there. So this is to bring the focus back on the Anderson-Mott story. What is happening to the electronic states here? I mean, is there anything different or more interesting here compared to what we saw in the parent Hubbard model? We noticed something unusual, that the optical and transport gaps in this not the materials, in the calculation seem to differ. You seem to find density of states where the optical conductivity doesn't pick up any contribution in a certain window. So we went and computed the IPR, the participation ratio, supposed to be indicative of degree of localization. So if you're in the metal 0.9 UC, the IPR is, and I am supposed to be looking at omega equal to 0, the Fermi level, the IPR is small, suggesting that you have extended states. Okay. If I go 2 UC or 0.9 UC, I see IPRs which at omega equal to 0 are like 0.1, suggestive of a localization length of a couple of lattice spacings. So the combination of orbital and spin disorder in the vicinity of the metal insulator transition leads to electronic states. Within this picture, you can still think of single particle states which are extremely localized. And if you go to the insulator, they are even more localized if you wish. If I increase JAF, this is to sort of put some of the blame on the JAF, I go to successively larger values of IPR. I can only do 6 and I can do 4, 6, 8, let us say. We tried 6 and 8, okay, but beyond that I cannot anneal the system. In fact, I can do 0 temperature calculations on larger sizes. I cannot do the finite temperature. So if I did just Hartree-Fock, I can probably do much larger sizes. But it turns out between 6 and 8, this trend is consistent. That the localization length is so short that the boundaries of the system don't seem to matter anymore. So JAF seems to play a sort of important role in the increased localization of this. Now you could ask, but you had a spontaneously disordered metal in the old pyrochlore. The old pyrochlore led to scattering and finite resistivity. But if I look at the IPR in the old pyrochlore Hubbard model, not this orbital spin business, I see nothing indicative of any localization. So it turns out, within the calculations and all the caveats, it turns out that the Moybdates model represented by spin and orbital fluctuations seems to have localization effects induced by the interactions in the problem, while just the Hubbard model does still have a finite resistivity phase and spontaneous disorder, but nothing that can quite be called Anderson localization of the electrons in it. So come to the conclusions. Hello. Conclusions. So, obvious statement, the Mott phase is a spin orbital liquid in the molybdates. The static approach, now this is the big caveat, suggests a spontaneously disordered metal, and the absolutely vital question is, if you did turn on dynamical fluctuations of the fields, the magnetic and the charge field, would it restore translation invariance at t equal to 0? Hard calculation. We can do perturbative sort of Gaussian fluctuations on top of this, but I don't know whether there is a clean answer that comes out. However, what one can argue is that even if translation invariance is restored below a certain coherence temperature, it's possible above that coherence temperature, these quote-unquote disorder effects still come back into the story to give you an unusual resistivity. To extrinsic disorder, which is inevitable in most of these materials, is likely to break the coherence and bring down the coherence scale, and again lead you back to the kind of phenomena you're seeing here. And of course, the disordered state, both in the theory and the experiment, can be field tuned. So the disorder, even if you could push it out through quantum tunneling processes, would resurface at finite temperature or be promoted by disorder, but then be annealed by an applied field. So that is the story. Thank you. Look, my lattice had a translation symmetry. Okay. So if I end up with a finite resistivity phase, something has been born and is randomly sort of oriented in this object. It's not a periodic thing. Okay. Periodicity one understands, but this is like a spin glass emerging out of a clean system. Yes.
Basic theory is unrestricted Hartree-Fock in a rotational invariant way with their
Zero temperature.
Yeah. You also mentioned that moments appear at what you called a UC1, and then there's a UC2, etc. So my question is this: if one did such a thing for the paramagnetic phase of the Hubbard model in infinity,
yes,
then the UC1 that you called will be the point at which moments first form, which is entirely an artifact of Hartree-Fock, and the UC2 that you get under those conditions is actually what is called the UC1 in the full theory, the DMFT theory of the Mott transition. In other words, you pick up none of the physics that between UC2 and UC1 in the infinite dimensional Hubbard model is associated with the real Mott transition.
Yeah. So
it slightly worries me that in that context, right? And this is a problem. I mean, where you don't have any long range order. So I think I can make the parallel to what happens in.
You don't even have short range correlations for that matter within that picture.
Yeah, but I worry that that's just an artifact of the Hartree-Fock side of the approximation.
No. Which side? Within the DMFT, there is neither long range order nor short range correlation. The single side version of DMFT,
yes,
done on a Bethe lattice, for example, would have no spatial correlations at all in it.
And it's purely the spatial correlations that generates your UC1 not equal to. I mean,
let me put it this way. So, why do moments form? So, within this kind of a picture, which is very naive, moments form because there is susceptibility which diverges. Okay. So, in his triangular lattice, there was a susceptibility which diverged at a particular Q.
Sure, but that will also happen if I mean, isn't that an artifact of the Hartree-Fock side of the approach?
No, that's okay.
The
So,
susceptibility is diverging because moments are first forming, yet moments are always there if you were to put in true quantum fluctuation.
no, I mean, the point is one doesn't have a better theory than Hartree-Fock to start with in this scheme.
No, I agree.
Okay, so let me start with this. My point is the distinction I make between the bipartite and non-bipartite, this kind of structures is, on a bipartite lattice, the chi-naught has a prominent peak, sometimes divergent. In the triangle, it doesn't diverge, so you need a critical U. In this case, it turns out that the chi-naught is a very flat object. So what local moments tend to form, they seem to have a distribution in width rather than a single value. And the nonlinear terms in the moment expansion, if you wish, tend to be important to stabilize the phase that you get there. Okay. So because there is no obvious ordering that comes in here. Is the stability of this that one is interested in? Would I get a metal with low energy fermionic excitations coexisting with this object? It's quite possible at zero temperature it's going to be wiped out.
I mean, that's my instinct.
Yeah, it's likely to be wiped out. Then the question is some variant of this. The point is, I put back classical fluctuations. My theory at finite temperature is not Hartree-Fock. So my suspicion is somewhere up in temperature, this physics is going to resurface once again.
I'm sure that's right.
Yeah.
My concern.
Yeah. So t equal to 0, I have the same doubts as you do.
Well, Your crystal field diagram
Yes.
reminds me a little bit of the rare earth nickelates, which are perovskite materials.
Okay.
In those materials, the electron lattice coupling is extremely important. For example, you get a bifurcation of the octahedra into two groups with different polaronic contractions of the octahedra.
Okay.
So I don't know anything about your molybdates, but I was asking you, do you think any such coupling might play a role in these systems?
What people have argued is not so much about polar-on physics, but they point out that bond distortions, which have the origin in the electron-phonon coupling, are actually responsible for the freezing of the spin system from a liquid to a glassy phase. Okay. So the fact that you get a 20 Kelvin spin glass temperature cannot be obtained without, it's been computed by people, without significant bond distortions. Now, so I am pretending that plays out only in the magnetic freezing sector and doesn't affect the electrons, which may or may not be true. But it seems that the major overall magnetic phase diagram doesn't seem to care too much about the electron-phonon coupling in the problem. The spin freezing does. Yes, Shubhra.
Local moments, the rare earth local moments.
Yes.
So usually for
Rare earth local moments have not been brought into the story at all.
so
Dhire.
yeah,
The molybdate has a spin half.
yeah, no, wait. So what's happening to this rare earth local moments?
Oh, the rare earth local moments are out of the story. They should be brought back. In fact, for some of the spin chirality issues, you need to bring back the rare earth local moments are weakly coupled to this magnetic subsystem, or so it is claimed. So, in fact, I should have added another degree of freedom on this with a very weak coupling to this S, let us say. So, this is a molybdate local moment. This is not a rare earth local moment.
Okay.
The molybdate has S equal to half, which I cheated and used as a classical moment. But there is also a S equal to 5/2, 7/2 sitting on the rare earths. It just so happens that its coupling to the rest of the subsystem is not that strong, but it's important for many of the anomalous Hall chirality related issues. But in this story, they have just been sort of completely ignored.
Pinaki again.
Thank you.